Hi, Professor. I will begin to introduce our final project about cancer detection. As we know, the treatment and management of breast cancer is determined by the disease stage, and breast cancer staging involves the microscopic examination of lymph nodes adjacent to breast to see if the cancer has spread. This process is fairly time-consuming and error-prone. But computer-assisted detection could increase the sensitivity, speed, and consistency of metastasis detection. Therefore, we decided to use CNN as the method to do metastasis detection. Actually, in this project, our work mainly contains three parts, including image processing, data augmentation, and model construction. Given a gigapixel pathology image, just like the slides, our goal is to classify if the image contains tumor and localize the tumors. Because of the large size and the limited number of slides, we want to train models using smaller image patches extracted from the slides. To get the image patch, we did the following job. We know that there are 8 magnification levels available per slide. Therefore, for every pixel in level 7, it corresponds to a 128 by 128 area in level 0. As the picture shows, assume the coordinates of this point in level 7 is xy. Then, the original point of this area is 128 times x, 128 times y. According to this, we extracted a 299 by 299 patch with the original point 128 times x minus 85, 128 times y minus 85. If the pixel in level 7 is positive, we label the corresponding patch as tumor. If the pixel is negative, we label the corresponding patch as normal. Based on this, we get some tumor patches and normal patch from tumor slides and using sampling strategy at first. As the results show, the number of tumor patch is much larger than that of normal patches. So we continue to extract some normal patch from normal slides to get a balanced training data set. Apart from this, to combat the rarity of tumor patches, we apply several data augmentations. We rotate the input patch by 4 multiples of 90 degrees, apply a left, right, and repeat the rotations. Then, we utilize the inception architecture in Inception v3 and a single disk layer on top of that model. We use the dropout to avoid overfitting and selected RMS prop as optimizer. After training, we evaluate our model on 3 images and drew the ROC curve for them. As the result shows, AUC value is 0.1921, 0.99 respectively, which are really high. It can prove the effectiveness of our model. In addition, from these heat map results, we also can know that our model can achieve a high prediction accuracy. In conclusion, we present a CNN framework to aid breast cancer metastasis detection in lymph nodes in our project. We built this model by leveraging a more recent inception architecture, careful image patch sampling, and data augmentations. Our method is state-of-the-art sensitivity on the challenging task of detecting small tumors in gigapixel pathology slides, reducing the false negative rate a lot and achieving a high AUC value. Our method also improves accuracy and consistency of evaluating breast cancer cases and potentially improve patient outcomes. So that's what we did in this project. Thank you.
Here are more details about our project and the code walkthrough. Our project contains three major parts, three major notebooks. The first notebook contains the whole process of training, test, and evaluation of the first model. And actually, we trained two models for our project. The first one we pre-trained on ImageNet, and the second model we trained from scratch and use data augmentation, including horizontal flip and rotations. And then we for the test, we evaluate the performance of two models using the AUC. We plot the ROC curve and then calculate the AUC. We have tested 3 slides for the first model, and then in this end-to-end script, we tested the second model with 1 slide. The task is to detect tumor cells in a very large pixel, in very large images. So the whole images can't read into memory, so we have to extract patches and make prediction and training on those patches. And actually, we are working on level 7, and since the downsampling is about 128, so actually for every pixels in the level 7 actually correspond to a region of 128 times 128 pixels. And then if we actually predict on level 7, we actually are predicting this region with a stride of 128. And then we treat as this region, we treat as 128 times 128 region as the center. And and we also need the context. According to the center, we calculate the corner of this context, and the context is 299 times 299, and we use this as context for the training and prediction. And if the center of the context contains at least 1 tumor cells, we will label these patches, this patch as tumor patch, and otherwise we will label the patch as normal patch. And this function we use to do this kind of calculation. And the second problem is that the dataset is highly unbalanced, so we have different strategies for to get balanced training set. We noticed that some slides contain less than 100 tumor slides. We see these kind of tumor and slides as normal slides, and we only extract normal patches from there, and we will extract both normal patches and normal patches from the first kind of slides. And we use this function to get all the statistics of the slides and decide which slides is the tumor slides and which slide is normal slides. And we use this first function to extract the tumor slide, which we extract both the tumor and the normal patches. But we will extract the number of sampled tumor patches is about twice of sampled. It's about twice of sampled normal patches. So the result of that is that we actually sampled about twice tumor patches than the normal patches after we run the first function. So we have to sample another half normal patches from the other 6 normal sites to get balanced data. So we use the second function and only sample the rest needed normal slide. Then we can get a balanced data set. After we get balanced data set, we train 2 models. One model is pre-trained on ImageNet, and we add flat layer, dense layer, dropouts layer, and do a binary classification. Train our model on all those patches using data generator to save the memories, since our data set is pretty large. And the second model is trained from scratch. And we also use data augmentations, contain rotation and horizontal flip. and is also trained on on the same training set. And for the test, we use this function to print the ground truths and compared with the predicted heat map. And this function is used to plot the ROC curve and calculate the AUC. Here is our results of the first model. We make a prediction on 3 slides. Here is the first heat map, predicted heat map. This one is the heat map, this one is the ground truth, and we plot the ROC curve and calculate the AUC. And this is the second test image, and the ground truth and predicted heat map, and the ROC curve. And this is the third test image. And the first slide we used to test the second model. And here is now the result, and is the ROC curve. In the second model, we use a script that can run end-to-end. We have already uploaded the weights and slide in that, and the script can run end-to-end. And our functions, we have already covered most functions we used in 3 notebooks, and here we found more details about other utility functions we use. And here is the result of the second model. Thank you.